Hello, everyone. We are Team 5 with Arlene Keith, Stephen Liu, and myself, Bruno Fu. Our final project focuses on the Child Mind Institute Detect Behavior with Sensor Data competition, which is hosted on Kaggle. This is a global challenge with over 2,000 participating teams and a $50,000 prize pool. The competition tasked us with detecting very specific behaviors known as body-focused repetitive behaviors. In this presentation, I'll walk you through the background, the device used to collect the data set itself, and the evaluation metric. After that, my teammates will cover how we process this data, built our models, and achieved our final result. Before we dive in, I want to note that our team has agreed to share both the slides of our recorded presentation for educational purposes after September 5th, 2025. Because this is a highly technical project, we'll be using a lot of abbreviations throughout the presentation. For example, IMU stands for Inertial Measurement Unit, which records acceleration and orientation. Earlier you heard me say BFRB, which is short for Body Focused Repetitive Behavior, the key behaviors that we're trying to detect. There's also TOF, which stands for time of flight. These sensors measure distance by sending infrared light pulses. We also have terms like F1 score, which is our performance metric, and TP, FP, FN for true positives, false positives, and false negatives. Having this glossary up front should make it a little bit easier to follow along. The competition is centered around detecting BFRBs, habits such as hair pulling, skin picking, and nail biting. These behaviors can cause physical harm and are often linked to mental health challenges like anxiety or OCD, obsessive compulsive disorder. The ultimate goal is to create models that can detect these behaviors from sensor data in real time. In a real-world setting, this would allow wearable devices to alert the wearer or caregiver when these behaviors are occurring, enabling earlier intervention and potentially reducing harm over time. The data comes from the Helios device, which is a wrist-worn wearable created by Child Mind Institute. It contains three main sensor systems: an IMU to track motion, orientation, and rotation, 5 thermopile sensors that detect body heat, and 5 time of flight sensors that measure the proximity of objects around the wrist. By combining these sensors, we get a multi-dimensional view of a person's movement, their proximity to their own body, and heat patterns, all of which are important for detecting BFRBs. The study design is carefully structured to create labeled data for training machine learning models. Subjects of varying ages wore the Helios device, and performed sequences of movements in 3 phases: transition, pause, and gesture. Transition being moving from rest to a target area, pause, a short period of stillness, and gesture performing either a BFRB-like motion or a non-BFRB-like motion. In total, there were 18 gestures, 8 BFRB-like and 10 non-BFRB-like. These gestures were also performed in 4 different body positions, which added variation and made the task more difficult. The goal was to build a model to classify and predict gestures based on the information obtained from the Helios device. For our training and testing hardware specifications, we use Google Colab Pro for training. Each session gave us a T4 GPU with about 12.7 gigs of CPU RAM and 15 gigs of GPU RAM. The data set is large with over 500,000 rows and 349 columns, representing all the different sensor readings and metadata collected. The test set has around 3,500 gesture sequences, and more importantly, about half of these only have IMU data, meaning no thermal or TOF readings. This forces models to be robust and work even when some sensor types are missing. The competition scoring metric is a combination of two measures. One, binary F1 score, and two, macro F1 score. Binary F1 score checks whether we can correctly classify gestures as target, BFRB-like, or non-target. Macro F1 score averages F1 scores all across the 18 classes. This combination rewards models that are both good at general detection and accurate in identifying specific gestures. And so by the end of module 13, we kind of tapered off at 1,667 out of the 2,400-ish submissions or teams prior to our FPVP. Here's a little bit more about the scoring metric. Precision asks if all the gestures we predicted as positive, how many were actually correct. Recall is more of all the actual positive gestures, how many did we detect. The F1 score balances these extremes in this competition. It's a high binary F1 would mean that we were reliably detecting BFRB like gestures overall, while a high macro F1 would mean that we were performing well across all 18 gesture types. The train and test CSV files store 1 row per time step for each gesture sequence. This means every frame of sensor data gets its own row, and together these rows form a complete gesture. There's 8 key columns, which are row ID, sequence ID, the sequence type, sequence counter, subject, gesture, orientation, and phase. Also, because this is a time series data, each gesture can span anywhere from a few dozen to several hundred time steps, depending on the complexity and length of the movement. The IMU captures linear acceleration in the X, Y, and Z directions, plus rotation as a quaternion in 4 dimensions, W, X, Y, Z. This motion data is essential because many BFRBs involve distinct movement patterns. For example, in figure 3, we can see the blue, which is representing the acceleration, and the orange light colors, which is representing the rotation. We can also see that we have some acceleration in the transition phase, then comes the pause, and then following the gesture, which is we can see with the repeated movement of acceleration oscillating up and down. The thermal pulse sensors measure temperature from 5 different points on the wrist device. The temperature measurements are different depending on the sensor location. Taking a look at figure 4, we can see an example of sensor data from a training set sample sequence. Once again, notice the pause phases between the transition and gesture phases. Also notice there's a drastic change before the oscillation of sensor data, similar to the acceleration, except this is with temperature. The Helios device also includes 5 time of flight sensors, each producing a grid of 64 proximity values arranged in an 8x8 pixel array. These are labeled TOF 1 to 5, V 0 to 63 in the dataset. The values ranging from 0 to 254, with -1 for no response at that pixel. At each time step, these readings give us a snapshot of spatial depth information essentially how far the wrist is from nearby surfaces in different directions. With 5 sensors positioned around the device, we capture a 360-degree proximity profile. This allows the model to distinguish between gestures performed close to the head versus those performed further away from the body, even if the motion pattern from the IMU looks similar. If we look at figure 5, you can see an example of TOF data across time steps 0 to 3. You can see how the pixel patterns change, brighter or darker spots representing changing distances in different parts of the sensor's view. These shifting patterns help the model recognize not just that movement's happening, but also where in space that movement occurs. In addition to the time series, motion, and sensor readings, our dataset also includes physical and demographic data for each participant. This comes from train demographic CSV and test demographic CSV, which each row corresponds to a single subject. There's 8 key columns: the subject, participant ID, adult, child, 0 for child, adult, 1 for adult, age for the participant's age in years, sex, 0 for female, 1 for male, handedness, 0 for left hand, 1 for right handed, height in centimeters, height of the participant, shoulder to wrist, centimeters, distance from the shoulder to wrist, and elbow to wrist, centimeters. These measurements are important because body proportions and demographics can influence gesture patterns.
Hello, this is Steven speaking, and here I'll cover our overall preprocessing pipeline. It consists of 6 main steps. It starts with missing data imputation of the raw sequence data, followed by sequence level aggregated feature extraction, and then we merge that with the raw demographic data by subject, and then we perform some more advanced feature engineering, outlier handling, and weak feature removal, and then lastly feature transformation and scaling in preparation for model training and prediction. So I'll go more in depth into some of these preprocessing steps. So for step 1, missing data imputation. So we decided to do this because we noticed that some of the sequences contain only IMU data, so there will be missing values for thermopile and time of flight sensor columns. And the competition also noted that there is known sensor communication failure within the hidden test data set, so that would result in some missing data for certain sensor fields. And so we decided to impute the missing sensor data using the medians from the training set, as some of the distributions from early EDA of these values were not normal, so we decided to go with the medians, and as that's more robust to outliers. And then step 2, sequence level aggregated feature extraction. Since the data is time series data, we noticed some more noisy fluctuations between time steps, and so we decided instead to compute aggregated feature statistics across a given sequence's time steps so that we could capture more broader trends and patterns specific to certain gestures with regard to feature value distributions. And so for the IMU columns, we took the mean, standard deviation, minimum, and maximum. For the thermopile columns, we took the mean and standard deviation by sensor, as well as the temperature range, which is the range of the mean sensor temperature across all of the thermopile sensors, and the temperature gradient, which is the standard deviation of that mean sensor temperature. For time of flight columns, we took the mean and standard deviation by sensor as well, and we also added a feature of sort of like a validation ratio, so that's the number of valid entries over the total number of total entries for a given sensor, just to get an idea of sensor reliability. So after step 2 of doing the sequence level feature extraction, we move on to step 3, where we merge the aggregated feature data per sequence by subject with the provided demographic or physical data, and any missing demographic data is imputed using the mode. And that is followed by step 4, which is more advanced feature engineering. And to start with, we have some thermal interaction features, such as the temperature difference between thermopile 1 and 4 temperature measurements, as well as the ratio between them. Also the temperature variance ratio, which is just the ratios of the standard deviations between thermopiles 1 and 4. We decided to go with these features because they would capture spatial heat patterns that can indicate hand proximity to the face, And we also noticed that thermopile data for sensors 2, 3, and 5 lacked predictive power according to the EDA, so we didn't really work with those temperature measurements when doing the thermal feature engineering. For some cross-modal features, we have modal movement heat coupling, which is the acceleration means in each direction the magnitude of that total acceleration times the temperature range, as well as the movement temperature sink. So that's the average standard deviation for the acceleration divided by the temperature gradient. And so these features would reflect any coordinated movements within the three directions of acceleration and heat dynamics during gesture execution. And we hope to capture that using the magnitudes of acceleration and the standard deviations. Moving on, we also perform more feature engineering for the rotation features, such as hand elevation. So that's the arctangent of the rotation with respect to the y-axis over the rotation with respect to the z-axis. So that gives us some sort of angle in which the hand is elevated or not. We also have wrist twist, which is the arctan between the x and the w axes measurements. And we also have orientation stability, which is the inverse of the magnitude of the rotation standard deviations in each of the directions. And so we chose these features with the arctan and quaternion magnitude formulas to quantify movement directions and rotational consistency. For time of flight interaction features, we have we mainly looked at time of flight measurements for sensors 1, 2, 3, and 4. Sensor 5 was seen as unreliable. So in order to get the overall activity and variance, we took the mean and standard deviation of the measurements from each of those sensors, just added together. And we also have a time of flight reliability score. So that's just taking the mean of the validation ratios that we extracted earlier to get a measure of confidence for these time of flight sensors. And these capture overall levels and variance within the central sensing area of the Helios device. And lastly, we engineer some dynamic features, such as gesture intensity. That's namely just simply the acceleration magnitude across the three directions, as well as the gesture smoothness, which is just 1 over the acceleration jerk, and the movement coordination, which is the inverse standard deviation of each of the acceleration standard deviations in each of the directions. And so with these dynamic features, we hope to capture gesture level motion and accelerometer statistics. So after performing feature engineering, we move on to step 5, where we handle outliers and remove any weak features. So any outlying values, depending on whether they're low outliers or high outliers, we clip them to the 5th and 95th percentile ranges. And we did this to reduce the influence of extreme values during training. We also removed any weak features, notably those associated with thermopile 5, such as the mean and standard deviation, as well as aggregate features related to time of flight sensor 5 and the rotation in the z-axis standard deviation. These features were removed from the dataset as they were predictably redundant and had low reliability, or generally had a lot of missing values. For step 6, after handling outliers and removing the weak features, we perform feature transformation and scaling in preparation for modeling. So we performed the Johnson power transformation for all of the features in order to stabilize the variance and somewhat normalize the features, and that was followed by standard scaling to prepare the data for model training and prediction. The transformer used and scaler used were fit on the features during training, and those same transformers and scalars are similarly applied to the new data during testing for consistency. And we encoded the target variable gesture numerically for model training. So while performing early EDA on our data set, we noticed a severe class imbalance problem. More specifically, that there are some classes that have greater amount of samples and some have less. And there's a 4-to-1 imbalance ratio between majority classes, which typically contain 640 samples, and minority classes, which contain 161 samples. And the minority classes are predominantly non-BFRB activities, and that can be seen in the plots on the right, where the lower number of training sample classes are generally non-BFRB in blue, whereas BFRB is in red. And this imbalance would directly impact the model performance for underrepresented gestures. And so in order to compensate for this class imbalance in our model, we decided to use base weights based off of inverse frequency. So minority classes would be assigned a weight of 4 or near 4, and majority classes would be assigned a weight of close to 1. And so this would give 4 times more importance to underrepresented classes. So in addition to weighing, we also performed some data augmentation for some of the more challenging or underrepresented gestures as well, in order to hopefully improve model performance. And we noticed consistently that the most challenging gestures with high error along with high weight were class 10, which is neck scratching, class 3, the eyebrow pulling, class 13, scratching the knee, and class 9, neck pinching. And we noticed some core issues in that there are similar motion patterns between challenging gestures, as they can be misclassified, such as neck scratch versus neck pinch have identical hand movements, and so they were often misclassified. Spatial proximity, like eyebrow or eyelash pulling, occur in adjacent facial regions, as well as limited sensor resolution, as time of flight sensors we noticed may not distinguish smaller differences between gestures. And so here on the right is our the weight distribution for BFRB versus non-BFRB classes. And so for BFRB classes, we have an average effective weight of 2.31, and we also had higher levels of data augmentation due to that importance, and so that would yield better overall performance, which resulted in a local score of 99.91% in the binary F1, which distinguishes BFRB versus non-BFRB. The non-BFRB classes have an average effective weight of 1.85, and this included most of the minority classes in the dataset, and this allowed us to achieve better performance on classification for those minority classes. They're simple actions like drink or glasses or texting. And our weighing strategy was that classes with higher weights would generally achieve better F1 scores. We did achieve perfect classification, F1 score for 7 gesture classes, and the overall model accuracy was 95.76% despite the class imbalance. Some limitations were that weights alone cannot solve motion similarity issues, along with extreme augmentation does not necessarily lead to better performance. So a little more on our data augmentation strategy. We decided to perform augmentation adapting to the model's relative performance for certain classes. So when augmenting, we would want to augment by a certain amount of times for each imbalanced class, and we augmented more for classes that are more difficult to classify. And so those more difficult to classify classes are given higher priority and higher targeted multipliers. And so for example, class 13, which is scratching your leg, that had the highest priority, and so we chose to augment that class by 3 times. Other critical BFRB gestures, such as classes 3, 9, 10, which are eyebrow and neck gestures, we augmented by 2.5 times. For those with moderate priority, like class 11, pinch knee leg, we augmented by 2 times. And for the rest of the remaining imbalanced classes, we performed a standard augmentation of 1.5 to 1.8 times. Now, in order to do the augmentation itself, we used a combination of 3 different methods. 40% of the augmented samples were produced by applying Gaussian noise. This technique added controlled randomness with an error of 0.02 to 0.03, and we assigned higher noise levels for problem classes, and this would encourage and simulate sensor variability. And the rest of another 30% was done with scaling, so we would scale in between a range of 0.85 to 1.15, derived from a uniform distribution, and that would account for movement intensity variations while preserving the general gesture patterns. And the last 30% was done using mix-up, which is used for within class interpolation only, and we used a beta 0.2 mixing parameter in order to help create more smooth decision boundaries between classes. And some thresholds that were implemented during augmentation was that a maximum of 3 times expansion or multiplier per class in order to prevent over-augmentation, and the target multipliers were derived from 1.8 times the median. The target for the overall data set was the
Hello, this is Arlene Keith speaking. Now we will discuss our model approach. After weeks of experimentation, our breakthrough came from implementing a dual model ensemble approach, where we built two completely independent neural networks. The first is our main model, which is trained on all 120 features from the multimodal centers, while the second is our IMU model using only 49 motion-related features. We needed two models to handle half of the test set that contains IMU-only data where time of flight and temperature centers fail completely. During inference, these models predict independently, and we combine their outputs using adaptive weights based on real-time sensor quality assessment. While we detect TOF sensor failures, we automatically increase the weight of the IMU model's predictions from 15% to 70%. Ensuring robust predictions regardless of sensor availability. This ensemble achieved a local score of 98.26% and pushed our Kaggle score to 70%, which was an improvement from our previous single model approaches that were stuck between 60 and 66%. So here we will explain further the main model architecture, which is a deep feed-forward network with approximately 85,000 trainable parameters processing 120 carefully engineered features. The data flows through a dense layer of 256 units where we implement an attention gate, which multiplies the output by a learned sigmoid activation, essentially allowing the model to dynamically focus on the most relevant features for each gesture. From there, we flow to 128 units with the JHU activation and batch normalization. Then to 4 units where we add a residual connection directly from the input to help gradient flow and prevent vanishing gradients. We continue down to 32 units before our final softmax layer where it outputs probabilities for all 18 gesture classes. Throughout the network, we use progressive dropout starting at 0.3 and gradually reducing to 0.15, which prevents overfitting while maintaining model capacity. Our feature set includes 49 IMU features for motion dynamics, 60 TOF features for spatial proximity, 12 temperature features, and 7 normalized demographic features. Training this model required a careful optimization strategy. We used the Atom optimizer with a one-cycle learning rate schedule that starts at 0.0002 and then ramps up to 0.006 at 30% through training, then uses cosine annealing back down to near zero. The improvement came when implementing focal loss with a gamma 1.5 and alpha 0.3, which specifically addresses our severe class imbalance where classes had 640 samples while others had only 32. This approach helped our training progress from 22% accuracy to epoch 1 to 87% by epoch 50. Our IMU model is deliberately smaller with 35,000 parameters, optimized for just 49 motion features. The architecture mirrors the same model but at a reduced scale, starting with 128 units that include an attention gate for dynamic feature focusing. From there, the data flows down to 64 units and then to 32 units where we add a residual connection from the input to maintain gradient flow. It continues to 16 units before reaching the final softmax layer that outputs the probabilities for all 18 gesture classes. We maintain the same progressive dropout strategy and JHU activations throughout the network to ensure consistent training dynamics within the main model. This model focuses purely on motion features, including 15 features for mean, standard deviation, and range across the XYZ axis. There are 13 gyroscope statistics and 14 derived features like jerk, smoothness, and our custom vertical dominance ratio that helps identify face level gestures. The model processes variable length sequences from 40 frames for quick gestures such as wave hello up to 300 frames for complex ones such as write name in air. Despite using only motion data, the model maintains an 83.4% accuracy, making it our fallback model when proximity sensors fail. Now for the results that justify our approach, where our local validation score reached 98.26%, combining 99.1% binary F1 for BFRB detection and 96.1% macro F1 across all 18 classes. There was an overall accuracy of 95.76%, and most importantly, for the BFRB detection, we achieved only 2 false positives out of 1,052 predictions and missed just 6 out of 1,056 actual BFRB instances. Our mean prediction confidence is 91.7%, indicating good generability. Our analysis indicated that the 7 gesture classes achieved perfect classification with 0 errors, including text on phone, glasses on off, and drink from bottle. The dual model ensemble provides robust fallback capability, automatically adapting when sensors fail. The only notable confusions were between physically similar gestures like neck scratching versus neck pinch, with 21 confusions, and eyebrow versus eyelash pull with 12 confusions, which even humans might struggle to distinguish from sensor data alone. Let me be transparent about our challenges, starting with RAM limitations that forced us to upgrade to Colab Pro when our feature engineering exceeded 12 gigabytes. More critically, we observed significant gaps between local scores and Kaggle scores, where early models achieved 85% locally, but only 40% on Kaggle. The breakthrough came from understanding how we handle TOF sensor values, where we initially treated -1 values as missing data and replaced them with zeros or mediums, which actually destroyed critical information. We discovered that -1 means no object detected in range, which is fundamentally different from detecting an object far away at a value, let's say 254. Preserving these -1 values, our Kaggle score had jumped to 70%. Let me elaborate on our exploration journey, particularly why traditional sampling strategies failed with our architecture. In week 1, we tried undersampling majority classes, reducing our data from 8,151 to about 2,900 sequences. But the model simply didn't have enough examples to learn subtle BFRB differences, and accuracy dropped below 60%. Week 2, we discovered SMO implementation, which creates synthetic samples by interpolating between minority examples, but this also failed because our features were aggregated statistics from entire gesture sequences. So when SMO interpolated between wave hello and write name in air, it created physically impossible gestures. Week 3 involved random oversampling with replacement, where we duplicated minority samples to balance the dataset. And while training accuracy shot up to 95% validation, it crashed to 45% because the model memorized exact duplicates, including their noise patterns. The fundamental problem was that traditional sampling assumes feature independence, but our features were highly correlated temporal aggregates, where you can't independently vary acceleration mean without affecting jerk and smoothness. The breakthrough in week 4 was working on the original sequence space with smart argumentation before aggregation, using Gaussian noise scaling and mix-up to preserve physical plausibility with those specific multipliers of 3.0 for class 13 and 2.5 for critical BFRBs, being empirically determined thresholds where performance gains plateau. Our model's main limitation is sensor dependency, where performance drops from 98.3% to 83.4% when TOF sensors fail completely, and the MIU-only model shows 36% confusion between spatially similar gestures like neck scratch versus above-ear pull. Computational overhead requires 130,000 total parameters and double inference time, which could impact battery life on wearable devices. For future work, we see promise in LSTM architectures to process raw sequences without aggregation, GAN-based generation of synthetic gesture sequences in the raw sensor space, and a self-supervised pre-training on unlabeled gesture data. Our work built on established principles from Zhang's mix-up paper and Lin's focal loss implementation, adapted for specific imbalance ratios. This project taught us that sometimes the journey through failed approaches like our sampling attempts provides the crucial insights needed for breakthrough solutions. Now here concludes our presentation, and thank you.